All right, today we're going to be scientific detectives. Our mission? To uncover the secret recipe of something you probably have in your kitchen right now.
I mean, you see it all the time, right? That box of baking soda in the cabinet. But what is it really? Like, what's it made of at the atomic level? And here's the cool part. Can we actually prove what it's made of with a super simple experiment? Well, the answer is a big yes, and that's exactly what we're going to do.
And believe it or not, this setup right here, yeah, just some basic glassware, a little vinegar, and our star of the show, baking soda, this is literally all we need to crack the chemical code.
Okay, let's dive in. First things first, we're investigating baking soda's secret recipe. Our goal is super specific. We want to find the exact amount of one key ingredient, carbon, inside a regular old sample of sodium bicarbonate.
Now, before we start mixing stuff and making fizz, there's one fundamental law of chemistry we've got to get our heads around. This is the key clue that makes this whole thing possible.
So this story actually starts way back in the late 1700s with a French chemist named Joseph Proust. This guy discovered a crucial, like an unbreakable rule about how the world is put together.
And here it is. This is our guiding principle, the law of definite proportions. It sounds complicated, but the idea is simple. A pure chemical compound is basically like a super strict recipe, one that never, ever changes. The proportions of the ingredients, always the same, no exceptions.
Just think about water, right? It's always H2O, 2 hydrogen atoms, 1 oxygen atom, period. Well, baking soda, sodium bicarbonate, it has a fixed recipe just like that. And we're about to use that very fact to figure out what it is.
All right, enough theory. Let's get to the fun part, the experiment. We're going to see how that classic science fair volcano reaction can actually help us gather some serious evidence.
So here's what we're working with. Super simple stuff, really. Baking soda and vinegar. But the most important piece of gear here is this precision balance. Why? Because our entire investigation hinges on measuring mass really accurately.
The procedure itself is super straightforward. First, we carefully weigh everything before we mix it all up. Then we let them react, the classic fizz, and after it's all done, we weigh everything that's left. And that difference in weight, that is our #1 most important clue.
Okay, so what's actually happening on a chemical level? Well, the sodium bicarbonate reacts with the acetic acid, that's the vinegar, and it creates a few things, but look at the very end of that equation. See that CO2 with the little G next to it? That G stands for gas. That's carbon dioxide, and that's the stuff that fizzes up and escapes out of the beaker.
And this is the genius of the experiment, really. That escaping carbon dioxide gas, it contains the exact carbon atoms we're trying to measure. So when we measure how much mass disappeared from our setup, what we're really doing is measuring the exact mass of the CO2 that floated away.
Okay, experiment's done. We've got our measurements. Now it's time to crunch the numbers. This is where we find the answer that's been hiding in our data the whole time.
And this is where being a good scientist comes in handy. You get organized. We record every single measurement in a data table, just like this one. You have to be methodical if you want a result you can trust.
So, in one of our runs, the final mass dropped by 0.78 grams. That's it. That's our lost mass. And we know that's the exact weight of the carbon dioxide gas that escaped.
But hold on a sec. Not all of that gas is carbon, right? It's carbon dioxide. But here's the cool thing. We know exactly how much a carbon atom weighs compared to an oxygen atom. It's a fixed ratio. So we can use that to figure out what chunk of that 0.78 grams is pure carbon.
So we run the numbers and bingo. The math tells us that inside that 0.78 grams of gas, there were precisely 0.21 grams of pure carbon. We found it. That's the exact amount of carbon that was hiding in our original baking soda sample.
Okay, we've got the mass of the carbon. We're in the home stretch now. Let's take the final step and see how our result stacks up against the known official recipe for sodium bicarbonate. All right, moment of truth. We started with 1.5 grams of baking soda. We found out that 0.21 grams of that was carbon. So the big question is, what percentage of our original sample was actually carbon?
The calculation is pretty simple, and it gives us our answer. Carbon makes up 14.3% of the total mass of the baking soda.
And now for the ultimate check. How did we do? Well, when we compare our experimental result to the known theoretical value, look at that! It's a perfect match.
Joseph Proust was right. The law of definite proportions holds up. Our little experiment worked flawlessly.
I mean, just take a second to think about what we just did. With vinegar and a scale, stuff you can find in a kitchen, we just proved a fundamental, unbreakable law of the universe. It means no matter where you get your baking soda, if it's pure, it is always 14.3% carbon by mass. Always.
And that just makes you wonder, doesn't it? This exact same law governs the recipe for everything. For water, for salt, for the proteins in your body, even for DNA. The entire world is built on these constant, unchanging recipes, hiding right there in plain sight, just waiting for us to figure them out.